Well, thank you very much for such a generous introduction, and thank you, of course, for inviting me here. It's a pleasure to be here. The topic for my presentation today, well, actually, the topic itself is a mouthful there, so let me just say what the talk is about. It's about asymptotic analysis. That tends to mean high SNR analysis, and the goal of that analysis is to gain insights into the capacity of wireless networks. So as was mentioned before, this is going to be a theoretical talk, so the focus is more on the capacity and how to gain insights into it rather than what's the latest technological standards for wireless networks. Okay. So as I said, we'll be talking about asymptotic limits a lot. So the world of limits, this asymptotia, or I think the better way to say it is some asymptotia, I guess. It's a very strange world where not everything is as it seems. So let's start with some motivation and also some notes of caution about things to keep in mind when thinking about limits. Well, first of all, motivation. Why do we even do asymptotic analysis? Well, the very obvious first reason is the principle of you must walk before you can run. So the idea here is that if you want to find or understand the capacity of a wireless network, if you cannot even find asymptotic limits or these first order approximations, then what hope is there of getting something more accurate in terms of understanding the capacity? So we must walk before we run. That's the first most obvious motivation. The second thing is what I call elephant matchbox doctrine. It's actually a legal term. What it really means is if you have a warrant to search for something big, that does not allow you to look into small spaces. What it means for our purpose is that, well, as theoretical researchers, we're all looking for some big idea, right? Some big new idea. And if you're looking for big things, it makes sense to look in places where there are big gaps in our understanding. And those gaps become very obvious when you do asymptotic analysis because it amplifies all the gaps that we have. So it's a good way of finding out where you might find something new. Okay. The third thing here, this is a quote by Victor Hugo. What it says is the beautiful is as useful as the useful, perhaps more so. And of course, what it means for me is that as theoretical researchers, often we are more in pursuit of beautiful results rather than useful results, but still it's helpful to remember that beautiful results tend to be useful in their own way because they inspire other further beautiful results, as we'll see as we go through this talk. Now let me also add some notes of caution because the world of limits is a strange world. The first thing you note is that when you work on these kinds of problems where you're always talking about asymptotes, there's this inherent ambiguity that you get used to, and that is the question, does this really matter or does it not matter? Right? Because on the one hand, you're looking at beautiful results from asymptotic analyses, and theoretically it's very satisfying and impactful perhaps. However, in a practical sense, it's hard to see the direct impact, at least not in an immediate way. So always there's that confusion or conflict at the back of your mind when studying asymptotic limits, how much these things matter. The next thing I'll point out is this is something to be very careful about when you take limits or when you take a problem and you say, okay, I want to understand this problem. Let's say I want to understand the capacity of this network. And you say, this is a very hard problem. Let me try to do asymptotic analysis. So let's take SNR to infinity, see what happens. Well, then what happens very often is that the character of the problem itself changes. You started with one problem, and yet when you apply the limits, the problem really becomes a different problem. So what you learn from there is not necessarily applicable to the original problem. So that's something you always remember. After the limits are applied, how much resemblance does this new problem have with the original one? And so reality is distorted when you apply limits. And for that reason, the last point is related to the previous one. Very often, the direct approach is not the most efficient approach when you're talking about asymptotic analysis, and we will elaborate on that later on in this talk as well. All right, so let's start here with, so information theory, of course, places a high premium or values very much exact capacity results because Shannon set a very high bar for everyone. And of course, those results are somewhat feasible when the network size is not that big. But once you start talking about large networks, for example, K users, then the size of the network becomes so huge. By the way, throughout this talk, this elephant will represent big things. So whenever I want to say something is big, you'll see the elephant picture there. So whenever you're talking about big networks, it doesn't make so much sense to ask for the exact capacity because if nothing else, there's too many parameters that define that capacity. So what ends up being more useful is to step away and take a look at the problem from a distance, ask for approximate capacity or first order approximations or asymptotic analysis. And typically a good starting point for that tends to be the degrees of freedom metric, which is just the capacity normalized by log SNR as SNR is allowed to grow towards infinity. And as I said, the motivation here is that, well, if you cannot even find the approximate capacity, then what hope is there of getting any closer? So let's start there. That's why it's a good starting point. The next thing I mentioned was the elephant matchbox doctrine. So if you want big ideas, you have to look where the big gaps are. And so let's step back like maybe 13, 14 years. You would notice that if you look at the K-user interference channel, this is where some of the big gaps were. So whether you have perfect channel knowledge at the transmitters or you have what we call finite precision channel knowledge at the transmitters, both of these problems were considered around 2005. And this was the state of art. On the one hand, we knew that it's possible to achieve 1 degree of freedom, which is somewhat a trivial thing to say, because after all, you can ask one user to transmit, and that gives you 1 degree of freedom. So achievability of 1 degree of freedom, straightforward. The more puzzling or frustrating aspect was that when you look at the outer bounds, the best thing that could be said was that you cannot do better than k over 2 degrees of freedom. And that seemed like a very weak outer bound. So the challenge, it seemed, was on the outer bound side. And there were a number of conjectures as well, all conjectures favoring the pessimistic conclusion that really the degrees of freedom should be just 1 for this network. Now, as we said, we know what happens here. These gaps were closed. Under perfect channel knowledge, the gap was closed in the optimistic way. So it was shown that k over 2 degrees of freedom are achievable. It's been a while since that. And the elephant, or the big idea that came out of this gap, was the interference alignment concept. And on the other hand, if you look at the other gap, what happens under finite precision CSIT, or channel knowledge? In that case, the gap was closed in the negative direction, meaning that if channel knowledge is limited to finite precision, really there's nothing better you can do than just have 1 degree of freedom for that interference channel. Now, what idea came out of that? The idea that came out of that was aligned image sets, and this talk is about aligned image sets, so that will be the focus of this talk. Okay? By the way, really, if you look at our papers, we call it aligned image sets, but here it was too tempting to make it more symmetric, so it's aligned images. All right, so we know that beautiful things can be useful. For example, interference alignment is a beautiful idea. It inspired many different kinds of schemes, ranging from asymptotic alignment to rational alignment, ergodic, blind, lattice alignments, beamforming-based schemes, delay-based schemes, improper signaling, delayed CSIT, alignment schemes for multiple hop networks, for partially connected networks, feedback-based alignment, and duality-based alignment, and something even last week that appeared, which is alignment based on some modifications of Reed-Solomon codes for distributed storage. So all these ideas came out of that. And also applications, because ideas often transcend applications, so very often you see the same principles being applied beyond wireless networks. So for example, the same asymptotic scheme that gives us the k over 2 degrees of freedom for the k-user interference channel ends up being the scheme that is used to close an open problem for distributed storage exact repair, almost exactly the same scheme. Similarly, the idea of topological interference management, which is the study of degrees of freedom of partially connected interference networks with only the knowledge of the topology of the transmitter, ends up being equivalent to the index coding problem, which is, of course, equivalent to a number of other problems as well. So that, of course, allows an exchange of ideas between these 2 problems. Similarly, the idea of blind interference alignment, which is based on creating and exploiting coherence patterns through either switching of antennas or just naturally existing coherence intervals, ended up being in some sense, the essence of the private information retrieval problem, leading to the capacity characterization of private information retrieval. So this is all to say how ideas can go beyond their immediate applications. And of course, by understanding something fundamentally allows you to see different things that seem unrelated in the same light, to see what it is that connects them. So that was all about interference alignment. From this point on, we'll be talking about aligned images. So what is this aligned images idea? How can we use it? Those are the two things I hope to get across in this talk. So to understand what aligned images is, the simplest setting we can think of is this two-user setting. And I will not go through the proof, but I will at least tell you what it says. So imagine you have these two transmit antennas, and you can think of it as a broadcast channel, so these two transmit antennas are fully cooperating, right? And then you have two users on the other side, let's say receiver 1 and receiver 2. And the goal here is for these transmit antennas, which are fully cooperating, to somehow create as large a gap in the entropies of the two receivers, of the signals seen at the two receivers, as possible. Turns out this is the essence of almost all interference channel information theory problems. If you could characterize this gap exactly at all SNRs, you would completely solve a lot of interference channel capacity results. Here, what we'll say is just asymptotically, what can we say about this gap? Okay. All right, so the main assumption here, so what is the assumption? Of course, transmitters are limited to power P. The main assumption here is that the transmitter, you notice that this channel is shown as dotted. What that means is the transmitter has only finite precision channel knowledge for receiver 2. What kind of channel knowledge he has for receiver 1 doesn't matter. It could be perfect, it could be just absent, or anything in between. It would not affect what I'm going to say. All right, so we want to maximize this difference of entropies. So transmitters, let's say whatever they can do, all the things they could transmit, let's just call them code words. It could be arbitrary anyway. So depending on what the transmitters send, the receivers will see a set of possible received values. Those are the images, that's what we'll call them. And of course, it's possible that for any given received signal value at Y2, at receiver 2, there will be multiple possible received values at receiver 1. And that is the essence of alignment. If you want to send information to 1 and not cause interference at 2, this is what you want to happen. You want to send as many resolvable different values at receiver 1, through which you can send information, while sending only an unresolvable, basically the same value at receiver 2. So this set, the number of different values at receiver 1 that correspond to the same value at receiver 2 is what we call the aligned image set. Okay. It is a random set from the transmitter's perspective, because remember, the transmitter has finite precision knowledge. It does not know exactly what this channel is. So it can only, based on the channel distribution, it can only say probabilistically what this set looks like. So this problem of maximizing the difference of entropies ends up being all about characterizing the aligned image set, or the size of this set. So you can show that the difference of entropies is bounded by the log of the average size of this set. And then aligned images is a combinatorial argument that tells you how large this set can be. And so it turns out, I will skip the details of the argument, it turns out that you can show that the average size of this set is of the order of log of P. And what that means is the difference of entropies is of the order of log of P, which is negligible in a degrees of freedom sense, because when you normalize by log of P, the log of P will disappear quickly. So what that does is it settles the pessimistic conjecture. Indeed, the degrees of freedom collapse, not only for the K-user interference channel, but also for the K-user broadcast channel as well. All right, so now it seems that we have learned a lot, because, of course, degrees of freedom, interference alignment, so many interference alignment schemes, and even with finite precision, we've settled all the conjectures. So are we now close to finding the capacity of wireless networks? Well, of course, we're far from it. And part of the reason is the degrees of freedom metric is just too fragile. And this is what I talked about earlier, this ambiguity of what matters and what doesn't matter is always at play. So for example, when we looked at perfect channel knowledge, we found all the nice things happened, everybody gets half the cake. Interesting ideas like interference alignment emerged out of that, but still, is it useful? Well, it's obviously this setting is too optimistic to be representative of reality. Similarly, when you look at the other end, when channel knowledge is limited to finite precision, suddenly everything just collapses. It's all doom and gloom there. And this is a pessimistic extreme, even though it does reveal some important ideas. So why is that? Well, it's because the degrees of freedom metric is too fragile. And let's look at that a little bit closely to understand what is it that makes it so fragile. So this is the standard degrees of freedom model. You have, for example, a 3-user interference channel. The outputs are as you would expect. Whatever is transmitted gets scaled by these channels, and then there's a power P that we scale, and that limit P going to infinity is what defines the degrees of freedom, asymptotic value. All right, so everything seems here very reasonable. However, there are some very obvious problems when you use this model and send P to infinity. Because what happens? It fails to capture, first of all, the difference of channel strengths. For example, you could have a channel that's just 10 to the minus 6, a coefficient that's very weak. Or you could have a channel coefficient whose value is 10 to the plus 6, like enormously large. But each of those coefficients is only capable of carrying 1 degree of freedom. Right? So any non-zero coefficient just carries 1 degree of freedom. So there's the distinction of strong versus weak is completely lost. And of course, that is okay if you're really interested in studying networks where all channels are comparable strength. Then it's fine to take that model. But especially if you're studying larger networks like extended networks, where really you don't want all channels to be equally strong, then it doesn't make sense to use degrees of freedom as the metric there. Similarly, degrees of freedom fails to capture another very important thing, which is the difference of channel knowledge levels. So just as we saw perfect CSIT, everything works great. As soon as you go to finite precision CSIT, even though finite precision CSIT is still a lot of channel knowledge, it ends up being as useless as if you had no channel knowledge at all. So what we're seeing is that a reasonable model at finite SNR, everything is finite SNR, becomes unreasonable when you take it to that infinite SNR limit. And that's the thing that we called before the distortion of reality in asymptotes. Now compare that to what happens in the generalized degrees of freedom method. So this is how that is defined. At first sight, this is what throws people off. This model looks completely unrealistic. Like, what does it mean to have these power exponents associated with each channel? So what we're saying is the power for each channel is really growing at a different exponential rate. Okay, that has really no practical way of justifying it. However, at the very least, and of course we'll see much more about why this makes sense, at the very least we notice that the two things that I pointed out, that the degrees of freedom cannot distinguish between strong channels and weak channels, as well as the fact that it cannot distinguish between different levels of channel knowledge, those problems are no longer there. Because of these exponential terms, the difference of channel strength is captured by these alpha ij terms. And similarly, the channel uncertainty level is captured by the beta ij terms. Okay, so what's happening here is quite the opposite of what we saw before. And now we have a model that looks completely unrealistic at finite SNR, and yet, as you let SNR go to infinity, it does capture some of the things we wanted to capture, a difference of channel strengths, difference of channel uncertainty levels. So to make this point more obvious, I'll use this cartoon analogy. So imagine, so finite SNR settings, you should think of it as if you have a target right in front of you. And of course, if you have the target right in front of you, the best thing to do is to aim directly at it. Right? It wouldn't make sense to be shooting somewhere else. And so that's what makes sense with finite SNR. But when you're in the asymptotic world, where SNR is going to infinity, now it's like shooting at a target that's far away. Now, aiming directly at the target is not a great idea, because you have to somehow compensate for all the distortion, gravity, wind, whatever else is going to happen, so that you have a chance of hitting the target. So often, what looks unreasonable at finite SNR ends up being the correct approach at infinite, in the asymptotic world. That's what's happening here. Even though this looks very strange, it is really just a counter distortion being applied so that when we go asymptotically to a limit, that limit would be meaningful. Okay, so now I said there's some kind of distortion, but why specifically that kind of distortion? Why those exponents? So let's understand the intuition behind that. So again, still staying with high-level intuition, imagine a network where you have these channels with different capacities, C1, C2, and so on. And this intuition comes from David's work, by the way. I think there's another paper I forgot to cite. Another paper by David and Guy Bressler, I think they talk about this intuition as well. So what happens here is, suppose I have this network, and now imagine that I scaled the capacity of each of these links by some factor gamma, the same factor gamma all over the network. What will happen to the capacity of the network? Well, the intuition says, and this intuition is true in all cases where we do know how to answer these questions, that the network capacity will also scale by this factor gamma. It's like if I inflated everything by gamma, then the capacity of the network should also scale by gamma. So what that means is if somehow the original network was hard to study, but somehow this inflated network is easier to study, then one way we could gain insights into the original network is by studying this inflated network's capacity and then normalizing by the inflating factor. That should get us back the original network's capacity approximately. That is exactly the intuition behind generalized degrees of freedom. So imagine, so that's the model, but imagine, just look here, and imagine you have just a regular Gaussian noise channel, a finite SNR situation. This channel has a certain capacity, let's call it alpha ij. And so what we're going to do is now scale the capacity by some factor gamma. And what is that factor? That factor is log of p. So the new channel will have capacity alpha ij log p. And that is this channel. That's the channel square root p to the alpha ij, gij, because when you, now in this channel, when you apply the limit p going to infinity, this channel will have capacity roughly alpha ij log p. Okay? And this scaling factor is applied to every channel in the network. And then, of course, you normalize by the scaling factor log of p. That gives you the generalized degrees of freedom. So what really you're trying to do is to inflate the network uniformly by scaling all capacities proportionately and then dividing by that scaling factor in the end to somehow get an approximate sense of what was the capacity of the original network you started with. That's a big distinction here. You're not trying to see what happens to the network as SNR goes to infinity. You're actually trying to find what is the capacity of the network at the original SNR, and you're doing that by applying limits and then somehow removing that by normalizing that scaling factor. All right, so now comes the main message of this talk, that this generalized degrees of freedom model gives us a practical opportunity to find the fundamental limits of robust interference management schemes. And what do we mean by that? Well, first of all, what are robust interference management schemes? Well, these are schemes that use mainly a coarse knowledge of the channel strength, but not so much the knowledge of channel phases, and they do not rely on, for example, the channels are remaining exactly constant across channel uses, so they don't require coherence either. So what kinds of schemes are those? Just the usual schemes, I mean, pretty much all the schemes that we think of as robust. For example, orthogonal access, treating interference as noise, multicast, CDMA, just multiple access, I mean, Gaussian codebook kind of schemes, layered superposition, rate splitting, space-time partitioning. I've seen the program here. There are some of these topics are very well represented at this conference. So those are all robust schemes, and we want to know what can we do with those schemes. As opposed to fragile schemes, these are schemes that rely very much on phase knowledge. For example, zero forcing or interference alignment, or even space-time beamforming, which requires channels to stay constant across multiple channel uses. They tend to be fragile schemes. Of course, this model is general enough to capture the entire breadth of all these schemes. But the important thing to note here, and you can think of beta here as a knob that controls how robust you want the schemes to be. So on the one end, if beta is 0, then you're restricting all schemes to this class of schemes, and you're asking information theoretically what's the best that can happen in that world. On the other hand, if you let beta go to infinity, then you're back to this perfect CSIT world, and everything in between is captured by the range of values of beta. All right, so this is the goal that I want to highlight. This is an opportunity to solve new interesting problems that hopefully will have more practical significance, even in the immediate sense. And that is to find the fundamental limits of robust interference management, meaning that set beta equal to 0. So you're focusing only on robust schemes that really use only the knowledge of channel strengths and see what are the capacity limits for those. So that's why this fancy banner up there is not really meant to glorify the results I'm presenting here, but rather the hidden challenges and opportunities in the open problems that lie in this space. So the problem, what is this space? It's a space of problems where we're looking at generalized degrees of freedom with beta equal to 0, meaning that these are schemes that only use channel magnitude. We want some kind of information theoretic guarantees of what are the optimal schemes in that class. So these are the 4 schemes I'll talk about. The first 2 I will just go through quickly because those are not mainly related to aligned images. And the goal here is to show what you can do with aligned images, but I also don't want to leave the impression that you need aligned images for everything. So the first two just show you that there are things you can say without using aligned images as well. Let's start with the first one. That's talking about orthogonal access. When is it optimal to just use something like TDMA? And the setting we're looking at here is called the topological interference management setting, where you're saying that the transmitter only knows the connectivity. So it just knows which receivers can be heard by which transmitters. That's the topology of the network, and nothing beyond that. So I'll just say what the answer is for this problem. So for example, you're given two topologies here, transmitters on the left, receivers on the right. These are the only links that exist. It's of course wireless, so you see interference and all. The message sets could be anything. Any transmitter may want to talk to any receiver that is connected to. And we're asking, when is it that orthogonal access like TDMA is going to be optimal for this network? And answer will tell you that, okay, for this network, TDMA is optimal, no matter what message set you consider, no matter what weighted sum of rates you want to maximize, meaning for the entire region. Whereas for this network, that's not the case. And what is it that separates these networks? It's this necessary and sufficient condition that tells you TDMA is optimal if and only if the topology that we see right here is chordal bipartite. And what does that mean? It's a simple condition that says that every cycle that can have a chord must have a chord. So there must be no chordless cycles. So obviously here it's optimal means this is a chordal bipartite graph, whereas the one here is not a chordal bipartite graph. And you can see that quickly by just, let me highlight the cycle here. So this is the only cycle in this graph. And you notice this cycle does not have any chords. So it's violating the condition to be a chordal graph. Whereas here you see another, I mean, it's the same graph except for this extra edge. With this extra edge, you have no cycles that are chordless because the cycle now has a chord. So therefore, this is a chordal bipartite graph. And for this graph, no matter what you want to communicate, TDMA will be optimal. By the way, just to make a minor point here, when we say that every cycle that can have a chord must have a chord, it does not mean that there cannot be any chords missing. So for example, this is a simple graph here. This is not a bipartite graph, but it conveys the main point. This is a graph where every cycle that can have a chord does have a chord. However, you notice, for example, there could have been a chord here that's missing, but that's okay. It's still a chordal network because it does not have any chordless cycles. Okay, that's just one point of reference. The second result, this is kind of old, 2015, so again, I'll go through it quickly. But again, this is something you can prove. It's a robust scheme, treating interference as noise, and you can prove these results without using aligned image sets. And the reason you can do that is because here, to prove the outer bounds, it's okay even if you have perfect channel knowledge. So really, channel knowledge at the transmitters does not make a difference for this scheme. That's why you can not use aligned image sets. So what is this? I need to go a little bit faster. So what is the optimality condition here? This is an interference network, and we want to know when is it optimal just to treat interference as noise. And what this says is if every desired channel is stronger than the strongest interference caused by the transmitter and the strongest interference received by the corresponding receiver, the sum of those two, and that's true for every user in the network, then it's a TIN optimal network. By the way, very often you see these optimality conditions. It's often, at least I find it easier to remember those conditions, to think of them in terms of the stable marriage, that kind of problem. So you have these kings and queens, maybe the kings are the transmitters, queens the receivers, doesn't matter how you interpret it. And these alpha ij's are the values that say how much they like each other. And then you want to know if the marriage is stable or not, those kinds of questions. But here, of course, it's an extremely stable. So you can think of the TIN optimality condition as a condition for a super stable marriage, because what you're saying is every king likes its corresponding queen more than the sum of how much the king likes any other queen plus how much the queen likes any other king. So that's a super stable marriage. That's one way of remembering the condition. And of course, once the condition is satisfied, we can find the degrees of freedom region for this network. I will skip this because I think I'm running a little bit behind the time here. And this is an old result anyway. So you can characterize the region based on these GDoF bounds, and you can plot it for 3 users. That's what it looks like. Um, and that'll be another point of reference that we will return to eventually. Now let's get to the main point here, which is aligned image sets. How are those bounds used? So for this, we will consider this problem. It is a k-user symmetric interference channel. Why is it symmetric? Because you notice that all direct channels have strength 1, meaning the exponent here is p to the 1. And all cross channels have strength alpha. So you see p to the alpha in those interference carrying terms. And we want to know what's the generalized degrees of freedom for this channel. So what do we need from aligned image sets here? Well, this is the thing we need, and we'll see how this very simple property will be enough to give us everything. So imagine you have a setting where you have k transmitters and 2 receivers. As usual, we want to compare the entropies of these 2 received signals. Receive signal 1 sees the signals, receiver 1 sees signals from 1, 2 all the way to k with strengths alpha 1, alpha 2 all the way to alpha k. So these are the exponents, right? P to the alpha 1, P to the alpha 2, and so on. Similarly, receiver 2 sees strengths lambda 1 through lambda k. As usual, what's important here is the transmitter has finite precision channel knowledge for receiver 2. It doesn't matter what happens for receiver 1. So what aligned images argument tells you is that this difference of entropies, and notice I'm simplifying things, this is actually a multi-letter form, and they should be conditioning on channels because receivers know the channel, but just to keep notation clean, I'm going to suppress those things. And also, we will use this, again, shorthand notation. Instead of entropy of y1, I will just write as entropy function applied to some kind of a vector, which is the vector of all these strengths, alpha 1 to alpha k. And similarly, entropy of y2, I will just write this strength vector, lambda 1 through lambda k. And what aligned image sets tells us is that this entropy is bounded by, or this difference of entropies is bounded by, if you do an element-wise comparison, just take a difference, so alpha 1 minus lambda 1, alpha 2 minus lambda 2, all the way to alpha k minus lambda k. Take the maximum of those, and if that happens to be negative, then just choose 0 instead. So that's what the 0 is saying. And that's the bound. That bound you get from aligned image sets. Okay, and then we see this bound is everything we need for this problem. Okay, so let's start with this problem here. Start with user 1. This is the usual mutual information. The rate is less than mutual information. You can write it this way. Now, the entropy of y1 is, it cannot be more than just the maximum of these strengths, the 1 alpha and alpha. The strength, the maximum of that is max 1 alpha log p. Again, I'm suppressing log p because in the degrees of freedom sense, we'll normalize by log of p anyway. So the term that we will get will be max of 1 and alpha. Now let's write similarly the mutual information for user 2. And you notice that for user 2, we've given him message 3 or message 1 as side information. Okay, so this is mutual information between y2 and w2 given w1, which of course can only help for the receiver to know the other message. It's still fine. Same thing for user 3. Now to user 3, we've given both messages 1 and 2 as side information. Now let's add these bounds. And now we're going to do these pairwise entropy comparisons, because remember, that's the essence of the whole thing. We want to use aligned image sets to use entropy comparisons. So we have this y2 given w1 minus y1 given w1. So let's look at here. y2 is right here. Its strength vector would have been alpha 1 and alpha. But now because it's given w1, that means I can remove x1. So therefore, it's just 0, 1, and alpha, because x1 is gone, because w1 is known. Similarly, for entropy of y, which one is this? y1 given w1. This would be, again, because w1 is given, so this will be gone. It will be just 0, alpha, and alpha. That's what that will become. And similarly, the next difference of entropies, we can write in our notation this way. And when you take the element-wise difference, 0 minus 0, 1 minus alpha, alpha minus alpha, the max of that, and if it's negative, then it's 0, that's this term. For each of these terms, we get 1 minus alpha plus, so you have 2 times 1 minus alpha plus. Okay, that gives you a bound. Okay, that's our first bound. Okay, let's go on to the next bound. Again, we start the same way. User 1, h of y1 minus, this is the mutual information. User 2, the mutual information given the message of user 1 as side information. Notice this time I'm not just bounding y1 directly by max of 1 alpha. Could do that, but it'll be more efficient to treat it differently. Now if I add d1 and d2, I'll see a difference of entropies. That's fine. I can use the aligned image sets argument to see that's at most 1 minus alpha, just like we did in the previous slide. But I'll keep these two terms as it is for now, because I'll find a more efficient way of dealing with them. So this was with users 1 and 2. I can write a similar bound for users 2 and 3 and users 1 and 3 and add these bounds. Now, when you add these bounds, it allows you to more efficiently compare entropies. So I'll compare h of y1 with h of y3, this one here. That's this first comparison. Then y2 with this y1 right here, and then y3 with this y2 right here. Notice that there's different conditioning going on here. So once again, because of symmetry, all these terms will turn out to be the same. So let's just look at the first of them. What is h of y1? That's just the vector 1 alpha alpha. That's this entropy. H of y, what does it say? Y3, given W2, W3, that would be this Y3. And we know W2, W3, so it would be just alpha 0, 0. Okay, that's the comparison. And if you compare them element-wise, 1 minus alpha, alpha minus 0, alpha minus 0, the maximum of that just is maximum of 1 minus alpha and alpha. Okay, that gives us our next bound, normalized by half. Of course, single user bounds are always there. You cannot do better than a single user capacity. And it turns out these bounds are enough to give us the whole some GDoF versus alpha. So this is what it looks like for 3 users. Just for the sake of comparison, because this is the famous W curve of the 2-user interference channel, from which the capacity of the 2-user interference channel to within 1 bit was found based on this. So you can compare what happens when you go from 2 to 3 users. Of course, there's something lost here. By the way, if channel knowledge was perfect, there would be nothing lost. With 3 users, you would get exactly the same GDoF curve per user as with 2 users. But because you have robust, you're asking for robust interference management, you cannot have interference alignment and so on, so you will lose something. Okay, you keep increasing number of users. This is what happens with 5 users. This is what happens with 10 users. And you can see as initially it was a W curve, but as you keep increasing the number of users, it's becoming more and more like a V curve. It's telling you really that when you have large number of users, really there's 2 things you have to do. If the interference is weak, you treat everything as noise. In fact, if this was a straight line all the way from 1 to this one here, that would be the line that represents treating interference as noise. And we're getting closer and closer to that as the number of users increases. By the way, number of users increases doesn't mean I'm asking that it should be infinity. We know exactly what happens for any number of users, but we just notice that it's becoming closer to that. And of course, if interference is strong, then everybody decodes everything, and that's enough for this. By the way, the achievable schemes are very simple. Just to remind you that we're not really trying to find new interesting achievable schemes here. Rather, the focus is on the outer bound, how to show that these simple schemes are the best you could do. There's nothing more than that in the robust setting. Okay? So that's the symmetric case. Of course, this, if you saw the derivation, that derivation could be applied to asymmetric cases as well. So that gives you this opportunity to go and explore what happens in asymmetric settings. All right, so that brings me to the last problem that we will look at. In this case, actually this one, we will look at the broadcast channel instead of the interference channel. The interference channel was for any number of users, k, but here we have only 3 users. So in that sense, it's more limited. On the other hand, the interference channel was symmetric, whereas here is completely asymmetric. All channels could have different strengths. So it's a little bit different situation. So let's try to see what we can say about this broadcast channel in a robust sense. So what do we need from aligned images this time? Because it's a broadcast channel, we will need a slight modification of the bound. This time we need a conditional form. So we want to, again, compare the entropies of y1 and y2, but conditioned on some variable w. And it's important, in fact, the most important thing here is that the conditioning is on the same variable. So h of y1 given w, it has to be h of y2 given the same w. And this w can be any random variable as long as when you give this random variable to the transmitters for free, the channel knowledge that the transmitters have for user 2 should still be finite precision. That's the only condition, that it should not give the transmitters knowledge of the channel itself. So for example, these could be messages. That's fine. That could be the conditioning. Everything else is the same. When you compare y1 and y2, you're just taking element-wise comparisons, alpha 1, lambda 1, alpha 2, lambda 2, and then if it's negative, then just make it 0. So we will also use this shorthand notation. We'll simplify the proof when we're comparing y1 and y2 with the same conditioning variable. That difference, which we can calculate easily, we'll just call it delta 1, 2 to make the notation easier. Okay, so now we're ready to derive the bounds. Let's see, to start with, as usual, receiver 1 we write the mutual information. The entropy of Y1 is bounded by the maximum strength of all the signals coming to Y1, and this is the asymmetric setting. So alpha 1 max is just the max of alpha 1, 1, alpha 1, 2, alpha 1, 3. That's what we have there. And this remaining entropy is just from the mutual information. For user 2, again, we're giving him message 1 as side information. For user 3, we're giving him messages 1 and 2 as side information. Add them up. Now remember, this is the broadcast channel. We can only compare things that are conditioned on the same variable. So we'll compare only those entropies. Okay. And we can do that, but it's much easier. Remember our notation, when we compare Y2 and Y1, that difference is delta 2, 1. When we compare Y3 and Y2, that difference is delta 3, 2. The only thing we care about is the conditioning is on the same variable. Okay, that gives us this bound. Of course, we could have permuted the users anyway, and for any permutation ijk, we'll have a bound like that. So that's one bound for the broadcast channel. The second bound is even easier. It's just 2 users, so you do the same thing. For first user, write the mutual information. Second user, give him message 1 for free. Add the two terms, compare these entropies. Notice that the conditioning is on the same variable, W1 in both cases, and this difference is delta 2, 1. Okay, that gives us the second set of bounds. These are 2 user bounds. Now the most interesting set of bounds is this last set, and this will completely solve the problem. So what do we need here? For every user, we're going to write 2 bounds. Okay, so for user 1, the first bound is a simple bound, just a mutual information. Rate is less than mutual information between the message and the received signal. The second bound is the one where we give user 1 W2, that is user 2's message, as free side information through a Genie. Okay, those are the only 2 bounds we need for user 1. For user 2, again, the first bound is a simple mutual information bound. The second bound is where we give him message 3 for free as side information. For user 3, again, the first bound is a simple mutual information bound. And the last bound, which is the second bound for user 3, is where we give him messages 1 and 2 for free as side information. So now we have 6 bounds. We'll need one more thing to complete this, and that is this observation that the mutual information between message 1 and the received signal Y2 can only become larger if I give W2 and W3, that is the messages for users 2 and 3, as side information for free. Why? Because whenever you add conditioning on independent random variables, it can only increase mutual information. You can rewrite this, just expanding the mutual information in this way, and add that as our last inequality. Now we're all set. This is everything we need to fully solve this problem. So let's add all those bounds and see what happens. Okay, so now we have 2D1 plus 2D2 plus 2D3 on the left side. What do we have on the right-hand side? Entropy of Y1. We can bound that as just the strongest of these signals, which is alpha 1 max. It's the max of alpha 1, 1, 1, 2, 1, 3. Entropy of Y3, what is that? Just the strongest signal at receiver 3, which is alpha 3 max. Strongest of those. Now we'll just do comparisons. So let's see. I can see here Y2 given W1 minus Y1 given W1. And this is the difference with the same conditioning variable. So that is delta 2, 1. So let's add delta 2, 1 to the bound. Next, let's compare these two. Again, the same conditioning variable, W2, and we're comparing Y1 minus Y2. So this would be delta 1, 2. So let's add that to the bound, delta 1, 2, right here. Next, compare this, Y2 and Y3. Again, the same conditioning variable. So this is delta 2, 3. That gives us, that adds to our bound. Then compare these two, alpha 3, entropy of Y3 minus entropy of Y1, the same conditioning variable. So it must be delta 3, 1. Add that. Now you notice h of y2 minus h of y2 cancels, doesn't change anything for the bound. These two terms are also just negatives of each other, they cancel. And lastly, this term that remains, that was just a noise term. It's a negative term anyway, I can drop it, but it's noise, so it doesn't really matter. That gives me the last bound. The sum of rates is bounded by this expression. And those are all, well, there's one more trivial bound you need, that is just a single user bound. Any user's capacity cannot be more than if that was the only user. So with these bounds, the region, of course, these bounds are true always, no matter, I haven't placed any additional condition besides the fact that this has to be the robust setting. So these are always outer bounds, but what's interesting is the region described by these bounds is achievable by a simple layered superposition scheme, and what that means is you're using Gaussian codebooks with different powers, and each codebook is intended to be decoded by different subsets of receivers. It's the usual kind of layering that you would do. That kind of a scheme, a simple scheme, a robust scheme, because it uses no knowledge of channel phases, is optimal, meaning it achieves this region provided a certain condition holds. What is that condition? The condition says, again, I will explain this more in the next slide. If I just say it in words, then you're saying of all transmitters, transmitter I is the most favorable to receiver I over every other receiver. I don't know if that really makes it clear, so let's look at it in the sense of the marriage stability kind of question. So what we're really saying is this. There were two conditions, these two. The first condition is just saying the king of hearts likes the queen of hearts more than he likes any other queen. And similarly, queen of hearts likes the king of hearts more than she likes any other king. Okay, that's basically saying that each diagonal term is the largest in its row and its column. The second condition is the more interesting one. What that says is if any king wants to be compared with another king. So let's say the king of hearts wants to be compared against king of diamonds. And he asks all the queens, how much do you prefer me over the king of diamonds? So really what we're saying is subtract the second row from the first row. That's how much you prefer the king of hearts over the king of diamonds. And then each queen gives him a score. The highest score he gets must be from his own queen, from the queen of hearts. Okay? So whenever a comparison is made between two kings, the king being compared, the first king, his own queen should give him the highest relative score. That's the second condition. If that is true, then simple layered superposition is optimal. So here you have the tin condition that we saw earlier, as well as the new condition that we just saw right now. If you look at these two conditions carefully, you will notice that whenever the tin condition is true, this condition is always true. That means this is a broader condition. In fact, if you look at a symmetric setting, because in general there are too many parameters, so you cannot really draw them all. But in the symmetric setting, I have only two parameters, A and B, for channel strength. Now in the AB plane, this the slanted lines, shaded region is the region where treating interference as noise would be optimal, whereas this gray region is a region where simple layered superposition would be optimal. Of course, one is optimal for the interference channel, the other is optimal for the broadcast channel. So that leaves us as the last exercise to do something interesting. Let's try this. So here's a network, 3-user network. This network satisfies the tin condition. So automatically it also satisfies the SLS condition. And because it satisfies both conditions, what it means is, for example, if I think of this as an interference channel, then treating interference as noise must be optimal here. Similarly, if I think of it as a broadcast channel, which means I allow all transmitters to cooperate, then simple layered superposition would be optimal. That would achieve the entire GDoF region. So how do those regions compare? So what does that mean? I'm really asking if I take this network in which, remember the kings and queens like each other a lot. This is a very super stable network. And I allow these transmitters to cooperate, how much will it help? So for the interference channel, we already know the region. For the broadcast channel, we can quickly find the region based on the bounds that we just saw. I will, the alpha max, of course, is just the strongest for channel that receiver 1 sees. It will be 2. Alpha 2 max will be the strongest for receiver 2, so it will be 1. Alpha 3 max will be 1.5. That'll give you the single user bounds. Then what are these delta IJs? For example, what is delta 1, 2? It's a comparison of 1 with 2. So to compare y1 with y2, let's subtract these. So 2 minus 0.5 is 1.5. This is negative. This is 0.5. The largest of these is 1.5. That's delta 1, 2. And similarly, you find all the delta IJs. Once you have those, you plug them into the bounds. You get all the bounds, the 2-user bounds as well as 3-user bounds. Write everything down. Some of them are, of course, redundant. If you, okay, let's ignore that. If you just remove the redundant bounds, these are the bounds you're left with. So now you have a region for what is achieved with treating interference as noise in the interference channel. That is the best you can do. And what is achieved by simple layered superposition in the broadcast channel, of course, that's also the best you can do. If you look at them visually, this is the interference channel region. This is the broadcast channel region. It should be bigger because, after all, broadcast channel cannot be smaller than the interference channel because you're allowing cooperation. And how much bigger is it? You can try to superimpose them. So now you see, of course, there's something bigger there. In fact, it's a 20% improvement in this case. So that's just to show as an example, not that this network by itself is very interesting, but just as an example how you can compare the GDoF regions. And remember here, we're only talking about for SLS for 3 users. So the future question here, again, the techniques that were used in the bounds, we believe they're true. And they are, in fact, we think you should be able to generalize this result to any number of users. We haven't yet found an efficient way of doing that. So it just takes too much work, and we haven't figured out how to make it feasible for a large number of users. So that's an open problem. But you can, of course, also make some more coarse kind of observations. For example, you could say if I have a network where treating interference as noise is optimal, an interference network, any number of users, where treating interference as noise is optimal, meaning it satisfies the 10 optimal conditions that we saw before. In that network, if I allow the transmitters to cooperate fully, what will I gain? Remember, this cooperation is a robust cooperation. So I'm allowing them to cooperate, but they don't have channel phase information. They only have channel magnitude information. And you can prove that what you will gain will be at most 50% for a network where treating interference with noise is optimal. So with that, let me conclude. It's a very high-level conclusion. What we're saying is that we saw that, as we saw when you do asymptotic analysis, you find big gaps. By closing these gaps, you find ideas such as interference alignment and aligned images. These are really two sides of the same coin. One of them is useful for finding new achievable schemes. The other is useful for finding outer bounds to show what is not possible. The opportunity here is to look at generalized degrees of freedom metric and characterize the fundamental limits of robust interference management schemes. That's what we focused on in this presentation. Of course, there's a lot more to this, especially if you allow beta to be non-zeros, and then you're spanning the whole gap of, on the one hand, robust schemes versus on the other hand, the schemes that use interference alignment and everything else, perfect CSIT, and you can bridge that gap using beta, and there's a lot more that aligned image sets bounds can tell you, which we didn't cover here. For example, some set inequalities and so on. But the main message here is that asymptotic analysis, true, it's very tricky, so you have to be very careful with it. But of course, it's appealing because it gives you beautiful results. And if you're careful, it can also give you useful results as well.
Thank you. There's time for a couple of questions from the audience. Very shy. So you mentioned from the information theoretical perspective. What about from a signal processing perspective, and what practical challenges people doing signal processing and practical comms in engineering can take from your talk and really go home and think and hope to contribute to?
So the purpose here, so there's always, in any information theoretic result, there's always the achievability side, and there's always a impossibility result, that an outer bound, right? The achievability side is where signal processing comes in, like what can we do, what kind of achievable schemes we can design, what kind of clever signal processing we can do to make better rates possible. So interference alignment schemes, for example, go into many different signal processing questions as well. On the other hand, the impossibility results, these are kind of negative results. These are showing you what is not possible. So these results do not go into the signal processing question. In some sense, they're saying no matter how clever you are with signal processing, this is just impossible. Right? So these are information theoretic outer bounds. So in a way, they're making the job of signal processing easier by saying, don't worry about it. It's just not possible.
Second question. I'll just end with 1 second one from my side. Recently in signal processing, the non-orthogonal multiple access has been very popular. How do you connect NOMA with this?
Yes. It's something, I have never really seriously looked at NOMA, but so my understanding of it may be flawed. But to me, it seems NOMA falls perfectly into this category of robust interference management schemes because the kind of schemes we allow here, which includes layered superposition and the multiple access channel kind of decoding, all those are it's roughly the same space as what you would consider in NOMA as well. And typically, the challenges that you see with these in practice is you have to deal with things like power control and how do you do the rate splitting if you're doing rate splitting, for example. And what these outer bounds do is they help you in that regard tremendously. So, for example, even something as simple as treating interference as noise, typically that involves power control because we're not just saying just transmit at full power and treat each other as noise. There's a power control involved. So if you try to optimize the power levels, that can become a non-convex optimization, get out of hand very quickly. However, once you know the outer bounds never have any power control variables in them, right? Because those bounds have already eliminated all those optimizations. Basically, you can think of it as a Fourier mode skin elimination. Similarly, when we talk about sort of simple layered superposition or any other such scheme, robust scheme, the outer bounds always give you a compact description of the achievable region, where all those decisions about what power levels to use, how to split the rates, those have already been optimized in that expression of the outer bound. So it gives you a way of eliminating a lot of those things and just seeing the final finished optimized result directly through the outer bound.
Thank you. So I think we'll go now. There's one question here. And then we'll go to the coffee break after thanking Syed again.
In the context of interference alignment, you briefly mentioned improper signaling. And then you said if we want to have something robust, we should not do something that is related to the phase. So does this mean that improper signaling will not be helpful when we aim at solutions like this?
Right. So, yes, because in the class of schemes that we considered for robust schemes, when I said these are schemes that do not use knowledge of the channels, in every case that we see, I mean, we're not, by the way, I should be clear, I'm not forcing this as a constraint on the problem. I'm not saying that, okay, transmitters are not allowed to use improper signaling or any other fancy scheme. I'm only saying the transmitter has, finite precision channel knowledge, which amounts to really not having phase knowledge. And then the bounds tell you what is the best that can be done under those assumptions. And those bounds end up being achievable in every case that we've solved so far with just the regular schemes using Gaussian codebooks, proper Gaussian codebooks. So you don't need any improper signaling or any of the other fancy alignment or even zero forcing schemes. Anything that requires phase knowledge is ruled out. So the focus is on really the robust schemes.
So this completes our program in the auditorium this morning, with last thanks to Professor Syed Jafar.
Thank you.